on, so I don't think he needs an introduction. He's been at NUS for several years, working on a variety of topics, and including 5G and 6G networks more recently. He has many Best Paper Awards and other awards to his credit. It will take a long time to go through all of them. He's currently also, in addition to being a professor, he's also the Vice Dean for Graduate Affairs. We're really delighted to have him here. We'll take some questions at the end, so hold your questions if you can, unless you want to have people ask you questions in the middle of your talk. We can wait. So without further ado, please join me in welcoming Professor Chan to give the keynote address.
Yeah, hi, good morning. So first of all, again, I express my thanks to the organizer of the APNet for inviting me today to be here to give this talk and to share some of this work that I have been doing. So this topic is kind of a special place in my heart because way back when I was a grad student in 1990s, my advisor was always very much intrigued by the idea of programmable networks. So he has been pushing us to look at this topic, and I must say, kind of is interesting to see how the field evolves over all this, all this era. Let me see, is that the right one? Okay. Can I use the mouse? The mouse is not. This one. All right, so just a just a quick kind of a background. So I guess even up to now, right? If you look at a network hardware, it's very much closed systems, and it's a classic, but you're still living in that era. When you buy a network switch, very often there's very little you can make changes to it. It comes with all the functionality, built in, and it's really hard to make changes. We have been trying to make all these things open source and everything, but it's not so easy to fight against the commercial interests. So of course, I say legacy. We think of it legacy as in how things tends to be. You have a fixed pipeline of network processing engines. When the packet comes in, you have the way to pass it. It goes through some processing, and then the packet leaves the number, right? So this part of it is very much fixed. You can't really do much to it. And on top of it, because you have a interface, again, this is more or less static. The ASIC is not available to you, and then you have a set of APIs. Cisco called it CLI, command line interfaces that you can write. But things are more or less the way it is. It's very hard to make changes. So we have been trying to hold on. The mouse doesn't work very well. Can I use the keyboard instead? It's easier to do this. Keyboard. Yeah, this one. Okay, I'll use this. Okay, I'll use the keyboard. All right, so we've been trying, since, at least when I was a grad student in the 1990s, we were intrigued that in that era, we think about making them more programmable. At least, some of the concepts are really being shared. You basically, first of all, you want a control plane where you can write code and runs, and you have a separation between the hardware and software, the control and the data plane, and then you have a standardized set of APIs that you can write on a control plane that controls how the data plane works, right? So this is at least the way we think about network that's programmable, and it's more or less very close to what we think of as the open flow and the SDN era, right? But one big problem in those eras is that there's no hardware, right? I guess those of us who are working on it, you buy ATM switches and try to think of a way to design a fixed API. So there was quite a bit of effort in certain groups. So we were actually having, at least my research group, we were thinking about pushing these things on the IEEE, and then the IETF as their own group. If you remember, this thing that the idea about these two is very similar to what OpenFlow does. It's defining interfaces, but there's no hardware, so things get a bit tricky. And of course, we were kind of in somewhat a state of I like to do something, but we can't make a lot of progress. I think the first kind of breakthrough was when SDN, as in OpenFlow came about. But we finally have a real platform, right? A real platform that you can try, and the underlying structures and hardware is pretty much the same. Okay, you have now the big difference is that you have an open interface for the control plane to write, to make modifications to the configurations of the underlying hardware. That kind of make it, you have now a standardized platform. You can write code and the idea is that it runs on all the switches. It doesn't matter what switches you buy, they expose the same interface, right? And then I guess it was really a big improvement based on what we were having for in the earlier era. So there's kind of the early excitement about SDN software defined networking. You write a code, it controls the entire network. Wow, right? But of course, what SDN, at least in that context, doesn't give you is that you are still writing code that runs on the control plane. You have no impact on how the core network functions actually work. You cannot really go and tweak the behavior on the underlying function, right? So I guess this is where with P4 and Pizza, the Tofino switches, that finally what I thought is that we can have a network that is more or less programmable, right? So the big difference here is that now you can actually directly access the underlying hardware with some constraints, of course, with a model, and Tofino adopted a more pipeline-based design because that design makes it more deterministic in terms of how the function works. So you have less flexibility, but more deterministic behavior. And on top of it, what is nice is that you don't even have to worry about having a standardized API on the control plane now. Because the API exposed is whatever code you write on the data plane. And once you have that, you can just basically now generate the interfaces. It's no more fixed. At least the thing with OpenFlow give you a fixed set of interfaces. Now the interfaces is function of what you write, right? You have the runtime, and now you think of it, now the data plane is programmable, and you compile it, you generate a set of interfaces that fits into your P4 behavior, and now everything is more programmable. You more or less get whatever you want to change in some sense, right? So I think this is where I think more or less what happened the last 10 years, a lot of excitement there. And of course, what are the benefits, right? I mean, finally it's more or less programmable to the extent that, that makes most of us happy. And a lot of the hardware behavior now becomes a software programmable functions. You can make changes now. And of course, for the researchers, we always say that, now I get more functionalities. What kind of exciting stuff I can do, right? So I guess the next thing is that, can we go back and take a look at a lot of the networking functions that we have been using? Can we redesign it in a better way because we have a new platform? Or are there even new things that you probably couldn't do previously? And now you can actually say, okay, I have a much greater capability. Let's do things in a different way, right? So I guess all these are possible. So basically it maps to what kind of functions, right, you think make sense. I think this is, at least when we start, this is really exciting. We finally have a way to think about how we can do things entirely differently and not relying on the hardware vendor to give you a set of instructions that you have to work on. You have a lot more control. So I guess this is where I'm going to share with you some of the work that we have done. All right, so I'm going to talk about three types of kind of work that I have done in the last, the last 7 to 8 years. So when we started, right, I must say initially when I look at P4, I wasn't sure how flexible it was. We were a bit skeptical. I'm like, is it going to be another SDN or whatever, which is great, but not really what I'm looking for. So I'm glad my future students were very persuasive. They said, let's give it a try. This is something new. You shouldn't be skeptical. Let's go ahead and try it. So now I have a new platform. We are kind of just trying to learn what we should do, right? So in fact, when I start, I say, let's have something that I think everybody will need, right? So what does everybody need in a network, independent of the application? So I started off with actually just time synchronization. I'll talk a bit more later. So I'll talk about three. So we started looking at the basic network services, which is time sync and in-network recovery. And then the thing I asked myself is that, again, look at something that that is independent of the applications, right? And then you look at network monitoring, right? I talk about some of those. And finally, we have to build some applications, right? Some network control algorithms. So I'll share some of the work we did on load balancing. And the last 1 to 3 years, I have been kind of looking at 5G network as a data center application. So we look at some of the 5G network applications, like how to do routing and hardware acceleration differently, using programmable networks in the 5G context, right? So I'll kind of go through them. All right, so first, time sync. Time sync has been, a lot of applications need time sync, okay, including the data center. So because there are existing, tools you can use NTP by the host, exchange messages, and then they agree on the time. But you realize that you realize that there's a lot of overhead. And one of the reasons is that if you want fairly high resolution time sync, I'm talking about, let's say, microseconds, you realize that the clock drift is about 20 parts per million, which is 20 microseconds per second. This is considered a decent crystal. So let's say 30 is the average. That means that if you want to achieve resolutions of 10 microseconds, you have to synchronize almost every second. It's a very high overhead, right? So NTP is around, but if you want high resolutions, maybe it's expensive. Of course, there's also even back then, existing some tools like PTP, whereby you can use the NIC card, the network interfaces, to do time sync, timestamp. That's possible, but the way that the standard is defined is that they actually mainly works on the NIC card. If you want a better time sync, it involves the control plane. Once the control plane is involved, when there's congestion, the accuracy tends to drift. And we're looking at very high accuracy, time sync. So it's very clear. I have a P4 switch now, right? It should be obvious that you can do better time sync because you can program every single stages. So when I started, I actually told my student, this seems like a trivial problem. You probably can get a poster done. Okay, but it works out to be a lot harder. Because there's actually not a single clock on the P4 switches. There are multiple clocks, and they are related in some a specific way. Plus, you think of hardware, at least initially you think of hardware, everything has to be deterministic, right? It should take the same amount of time to go through all the stages. So offsets are easy to compensate for. It's not true. Even the hardware, you're talking about nanoseconds level, the stages do differ depending on the exact payload you have. So different payload will have slightly different processing time in the hardware on the orders of tens of microseconds, right? Because your clock is 1 gigahertz. So all these things actually make the problem a lot harder. So this is what one of the first long paper we published on SOSR. I think it was the best paper that year 2019 because it's easy logically, much harder to do it in practice, right? And I guess we did it. And one of the good things is that by doing this, we actually learn what are the constraints, logically things work like this, but there are a lot of practical constraints that we kind of pick up, oh no, this is actually one is a bit easier to implement on the hardware, sounds more logical, but a bit harder, right? So we kind of learn by actually doing this. So this is kind of, I'm going to show the results, I'm going to show that, you can actually go to the level of tens of nanoseconds. Time sync, right? Of course, as you go further away, if the switches are 4 hops away, your accuracy drops. But overall, this is, I guess, on average, you get a fairly good time sync. So we actually open source the code. I think there were some groups that were actually using it in the test, including Eating. She was using some of our code to do some of the work for her optical stuff, right? So so after that, we move on, and I guess. One of the things you work on is that besides being interesting, I need students who are very excited about the problem. So they came to me and say, Prof, let's look at link failure, right? I said, why link failure? Because link failure is that when there's a problem in the network, you should fix it in the network, right? Because usually you think of something fails, okay, first some mechanism will detect the failure, right? And it takes some time because even if the link fails, talking about hundreds of nanoseconds or few microseconds, it takes time to detect. You cannot just assume that things go bad. You need to wait for a while, right? You detect it, and then of course once you know that there's a link failure, you want to change the route, right? Change the route, and you choose another route, and then after that you have to recover, right? And of course, if the switch is not involved, the recovery can only be done end to end. Once you've done end to end, it is a lot slower, right? You introduce a lot of long latency, you can go into timeout, right? So I guess that once you have packet loss in the network and you deal at the end host, you naturally will have a lot longer delay, and that leads to, and if you allow short flows, a much longer flow completion time. So we say, well, the rest, detection is a bit hardware, choosing a route is routing, they're all interesting. But what we can do in the network is we can do local recovery, right? So we call it, in-network packet loss. So again, how do you do in-network packet loss? Because that requires amount of caching, buffering, and timing management and retransmission. And normally the switches don't do that, right? You always do it end-to-end on a wireline network, because the assumption is that there's very little packet loss in the network. It's going to be a small problem. But as you go higher and higher speed, your data centers requires higher performances. Even a small amount of delay here and there adds up, right? So you said, I can do it in the network, why not? In fact, this is usually done, I'm not sure, more commonly done in the wireless network, because they have much higher loss. So kind of the underlying techniques is known to us because it's done in the wireless, right? But to do it in a wired network with high speed, it's not so common. I guess it's like, how do you cache a packet? There's no caching, at least in the beginning, right? And this is not like data caching, do lookups. You are caching packets that you have just sent, right? So I guess I argue that if you can do it, this is the right place, because you hide the loss from the endpoint, and the recovery is much faster, right? All right, so kind of your goal is to mask the effect of the packet loss for the endpoint, do local recovery, and it was still early. I think if you propose this idea now, people will complain. But back then it says that you can actually cache the packet by using a loopback. You loop the packet back within the switch, and then you just have to cache. You do the caching by packet, by doing packet circulation, and you only need to cache enough to handle the time it takes to detect the loss and configure a new route. This is the timing. It's not very long, and you don't have to do it for every single route. You do it for the routes that you think are very important, or routes that you think are more prone to loss, right? So if you are more selective, and your time of caching is rather short, because it's the time it takes for your packet to reach the next switch. So it's one hop. So it's much shorter. All right, so roughly, you have the switch data plane, then you have a buffer and queuing engine. So the challenge is that the default queue is FIFO, and there's, even on the P4 or Tofino, there's not a lot you can change on it. You have later on Tofino 2, you have some priority queues. So you don't have the right queuing discipline, right? So as I mentioned, I jumped ahead. So you actually cannot use the routing algorithm. Your goal is, the way we did it in SQR is that if you want to protect this particular link, you loop the packet back. So you do consume some bandwidth, right? And because of that, actually there are a couple of challenges. Okay, you keep the recent copies, okay, and you need a timer to know that how old this packet is, and that this packet probably already has reached the other switch because there's no link failure signal coming back, and then you can throw it away, right? And this is actually possible, even on the earlier, the initial version of Tofino, it already can be done. And this can be done, So what are some of the challenges? Right, first, you need to keep track of how old this packet is, so that you can throw it away when it gets too old, because you need a sense of time. And plus, you cannot just loop back on a single port, because that port might be very congested. So the way to do it is that you have to distribute this packet circulation onto different ports. Because if you keep looping on the same port, you actually increase the link utilization. You might introduce packet loss. So you have to share this load. The assumption is that there are sufficient spare capacity on one of the ports, or some of them on the switch. And you use those spare capacity to do this packet circulation. So you have to, again, in runtime, figure out what are the ports that are free, and you do it, right? And then, okay, you can build it. So this actually works quite well. It's one of the earlier work. So SQL looks at link failure, the link fails. So we have a more recent work published 2-3 years now called Link Guardian that handles query failure. But basically, the link doesn't fail. You just have higher bit error loss than others. And there's a way to kind of do some protection on that link with higher link failure rate. Right? Similar high-level idea, but the details are quite different. Like I guess I won't go into this. Okay, I guess I'm thinking probably too slow. Okay, next I'll talk about network monitoring. All right, so network monitoring, I guess, if you're familiar with this, one of the core components of network monitoring is sketches, because you can't monitor all the flows. So you need a data structure to kind of do approximation counting. So I guess I'll go into what's the sketch algorithm and count mean sketch. But the idea is that you have a data structure that you can use to track the packet traffic statistics, right? So one of the kind of the limitations of count mean sketch is that they use the same. They tend to use the standard algorithm, use the same memory size for all the flows. But then we know that in many cases, your traffic flow has the elephant and mice thing, right? A lot of mice flow, very small flow, and a very small number of elephant flows. So if you think about bit efficiency, you need more bits for the elephant because the counts are larger. You actually only need a small number of bits for the mice because they have very small count. But when you start, you do not know, right? So by default, all the counts are the same size. And this is a problem because it means a large number of the flows, you actually underutilize the bits. You have a size that is way too big for the mice, and there are a lot of them. So people are aware of this, so they say that one of the way to kind of get around this is to so-called separate the mice and the elephant. So for example, one of the paper called Elastic Sketch, they have a sum structure in front to say, let me know if they will detect the elephant flow first. And then the rest will be mice, right? So that the elephant part, they can use a larger memory, bits per flow, and for mice, they're smaller, right? So this kind of works. The data structure makes sense, but actually not trivial to put it in the hardware. The key thing is that this should run in the data plane, and to run in the hardware, they kind of work, but they have to make some compromises when they put in the hardware, and then if you run it in the hardware, it loses some of the efficiency. So what we did was that, can we revisit this with P4? Because the P4 is a pipeline architecture. Can we design a count mean data structure that is actually more friendly to a pipeline data structure? So what we came up with is like, okay, so the problem is that I need to use different sizes of bits for different flow size, right? But I do not know how big they are at the beginning. So let's think of it this way. At the first level, everybody is small. I use a few bits. And then when they overflow, they are medium size. Then they go to the next level, which I have more bits. And then as they go bigger, they overflow, they will hit the large one, right? So we organize it as from small to big. And the good thing is that every level is actually a pipeline. So think of it, it maps fairly well into how the Tofino pipeline stages work. So the first stage go for the small, next stage go for the bigger ones, and then you keep going. You can have 3 to 4 stages. And this architecture, this structure, actually doesn't work very well in software. We do it in software, it's a lot slower because it's less parallelism in software. But in hardware, it actually works exactly the way the Tofino was designed. So in some sense, we kind of say that, well, we have a data structure that's designed for the hardware, which I thought was interesting. Like we didn't just take a software algorithm and try to squeeze it into the hardware. We started with what makes sense for the hardware and design it, and it's much easier to implement at the end. So I won't go into the details. I'll just show you roughly how it works. You count this case. Zoom keep coming up. Okay, so. Alright, so if it's full, you go to the next level. So I guess I do very quick elimination. So at the end, when you ask a query, you will just go traverse the tree and you will stop at the level by it did not overflow, right? And then you can get the answer. I guess I wouldn't spend too much time here. Roughly, you do the counting on the data plane. That gives you a certain amount of data from the counting sketch, and then you send the data back to the control plane, which do more processing for the more intensive stuff. So we actually did comparison. Actually, I think it's actually quite a good algorithm, especially when you run on the data plane. So kind of what I emphasize here is that when you do monitoring, the hard part is always that I want to look at a lot of things. So if you look at a single objective, you can always find a very good algorithm that's very good for that particular task. But if you want a universal counting that's good for different things, it's always a trade-off, right? You gain some, you lose some. So even for FCM, okay, VD includes additional data structure. You find that if you actually add it, called a top K in front, it actually works even better. But not in all cases. In some cases, it actually works. So a lot of this counting sketch is always a trade-off. How do you do better and overall, and not say if I do one thing very, very good, the problem is somewhat different. It's in some sense slightly easier problem. Alright, so in this case, we designed a data structure that works for the hardware, but it's on a single local switch, right? So you ask yourself, what you would do debugging and monitoring the network, you want to know the entire network, right? Not a single switch. So how do we use this switch in programmable to detect network level, right? So we were looking for a hard problem, and what we came out and said, okay, how about microburst? Microburst is known to be hard because it is something that happens over a very short time, 10 to 100 microseconds, because of some short-term, intermittent timing problem or very short-term congestion. And this happens in the network for various reasons, but how the network works, right? So again, it's hard because it is occur of a very short time scale. So if you are using monitoring tool, even a sketch that average over like 1 millisecond, you might not see anything because on the average things are fine. But over a short term of hundreds of microseconds, there was a problem and there was packet drop, right? So how do you detect such things? Because they are so short term, they happen only suddenly, and once you average them out, the problem goes away. How do you do it? And then it's unpredictable, you cannot constantly look for it. So if you're like, well, we have a programmable switch, can we kind of build some kind of like you drive the car, you have a dashboard, right? You have a recording. Can we build some kind of a recording, that basically let you see everything, and that you also have history, because when the car accident happened, you want to see 5 seconds before the car accident happened, who drove, who did what, which car drove which way, right? I want to know the history. If I only see the problem, it's too late. Oops, okay, I'm running so fast. Okay, so anyway, so we did, and basically the idea is that, let me see. You basically store, similar to SQL, you store a certain amount of data, history, on the switch. And here, because we're using Tofino 2, we don't need to do switch anymore. You can actually use the actual buffer, and you can actually use the queuing mechanism to cache some part of it. And what you have is that when you send data, they get recorded, again, the most recent, in this case, like 1 millisecond. You store them on the switch, and then what happens now is that if you have a problem, right? For example, you program the system, if any of them detect a microburst, defined to be, let's say, the queue length exceeding 80%, you will trigger, you have a fan here, you trigger on one of the switches that detect a microburst, and that switch will now trigger a signal, the red pockets, like whoever send me any data should now snapshot whatever is in their cache, and then send it back to the collector. And remember, everything is time synced, because remember we did a work on the time sync. So you have a very good time stamp on all the switches. And once you do this, think of it, it's expensive, but you get a very, very detailed record of what happened right before the problem. And you don't need a lot of time, because on data centers, very short latency, you don't need more than 1 millisecond of data. But you have it on all the switches that plays a role. So what what's interesting is that when we did this work, sending for submission, what the complaint that people have is that, the system, okay, makes sense, and all your evaluation is you know the problem, and then you build it in a test bed, and you show that you can detect whatever you insert, right? Say it's not real. If your system is really good, you have to find problems that you didn't know even exist. Then I'm like, how do I do that, right? I didn't know it exists. How can I find a problem? So I told my student, luckily students are very brave, they said, let me just run it for days and weeks until I have a problem. So this is what we did. We just let the test bed run for like 2 weeks. So finally it came back and said, oh, I found it. I see a microburst. And in fact, it's interesting because the way the microburst happens, is two sets of applications interacting. Then if you look at one of them, you will never see it. You only realize what happened because we have our system running, that another flow running in another part of the network causes some burst, which then cascade to this application. So I think, at least I was quite happy because the system actually could detect something, but it takes us at least 2 weeks to find the bug. And it was, but it's about fuzzing now, right? You run fuzzing, you should supposed to find bugs that you didn't know exist. So I'm glad we found it and the paper get published. So anyway, so this is the way it works. Right, okay, I'll go on. The animation takes time. Okay, so we can use it for actually other things. We believe that anything you do with timing and high resolution, this will be useful. Okay, so I guess, all right, I speed up a little bit. Okay, so I now look at applications, right? So I tell you about the services, the monitoring now is things that we did on building an application. So first one is for load balancing. This is again data center. So, right, we know the RDMA is the thing that everybody's using now. And because RDMA gives you the good performances, very versatile, and I guess is widely used right now, right? So I guess I probably don't have to talk about why RDMA. But at least when we did the work in 2002, kind of still true now a little bit. RDMA is very particular about timing and packet loss. And because of that, they don't actually works very well with when there's a multi-path protocol. Because if you have multi-path, you will introduce some amount of packet reordering. RDMA will treat it as packet loss, then it will back off and causes quite a bit of problem, right? So in fact, the ECMP, which occurs, is very static, and other routing algorithms don't, at this point of time, don't work very well for RDMA. Maybe I can just say it. So think of it, you have do load balancing in the data centers. You have per flow on one end, right? This is kind of very cost string, and then you have per packet string, and something in the middle is folded like Conga, right? You look for gaps in the applications, right? ECMP, of course, is still widely used. It's easy to so-called, it's something you know, right? It may not give you the perfect load balancing, but its behavior is known to you. When you have elephant and mice flow, it doesn't do as good a job in distributing your flows. And per packet, of course, now packet spraying is getting a bit more, talk about. You can spray the packets, but you have to handle all the out of packet. Right, and that can be tricky depending on the exact hardware they're using and your assumptions and your applications. Because in the middle you have your flowlet, and which has shown to work rather well for TCP because there are gaps between the TCP flow. But RDMA being more hardware accelerated, there are actually less gaps there because it does a very good job in sending packets continuously. So if you're looking for gaps in your flow, whereby you can do rerouting, the gaps don't really exist as often. So now you're stuck with RDMA, you get a better end-to-end performances, but your load balancing is not as good now, right? So what can we do, right? So if you look at this axis of the X and Y, one is how much packet reordering you have, and how fine grain. You want very fine grain, and you want to be packet always in order. So of course, per packet will be potentially, if you don't do a good job, you have a lot more out of order packets. And those that we tend to look at is we want in order, so we have less opportunity. So okay, so what we did was that we say that, again, we have the programmable switch. Can the switch help you? Right? It should be, right? But if the switch help you to do packet rerouting, the underlying assumption is that it is rather hard to ensure. Our goal was that I want almost no packet out of order. So, but you cannot ensure that you have no out of order packets if you have arbitrary path, right? So we want to have more chance to change your path, but we want to be able to ensure that the way the packet, the amount of reordering is controlled, is kept. So this example is that if you don't control, you have 3 packets in front, you are very unlucky, they go to 3 different paths, and the 4th one arrive, right? And now you potentially need many queues to handle the out of order packet arrival, right? So the way Conway did is that there are many other details that actually are still important, but I thought one of the things about how we use a programmable switch is that we use it to control how we do rerouting. So the idea is actually quite simple, right? You have an existing route that's congested, you want to change, so you send the last packet, this is the last packet on this path, and then after that, okay, you can switch to the new path. But if the new packet on the new path, which travel on a less congested route, reach that earlier, you put it in a separate queue. Say stop, pause, okay? And then you will wait until the last packet from the previous path goes through, then you release all these guys, and then now you can release all the resources back to 1. So you need 1 extra queue because at any time at most 2 paths. But the more paths you allow, the more queues you will need, right? And of course you have to put it together, there are some other details that I will go through, but basically this is one way we have able to use the switch because it's agnostic to the endpoint. It's just switch to switch, top to top. And you can use, you can switch path, in a more flexible manner. Okay, so the last topic, very quickly, I'll just talk about 5G. I guess maybe if you're not into this, I can motivate you is that you can look at the 5G network as evolving like the SDN. They want to be more open. They want to use more cloud technology. So the internal, instead of getting a single big box, they're moving towards this so-called separation. You have the central unit, you have the distributed unit, you have the radio unit, right? So this is a good opportunity because it becomes yet another data center-like application. So a lot of problems actually you can redo. Okay, you can redo. So one of the things is that the original design, even up to now, is a very static, kind of point-to-point connections between the different components. So actually when we did it, it was obvious to us, you need flexibility, and with a tree topology, it's not very flexible. You want routing inside the WAN, and they don't have it, right? It's in the standard, but people don't actually do it, because doing it needs quite a bit of changes to how you think about the network should be built. So we show that actually you can actually introduce routing into the WAN. Of course, and there's actually some advantages, but the key thing is that you have to really know how the internal works because there's a specific way the packet is scheduled, there's a specific time the packet will arrive. And this is where your P4 works because your P4, you can change the routing table in runtime in the data plane. So you can actually get the schedule and go and modify the routing table in the switch in the data plane in the orders of like sub-milliseconds, so that within 2-3 milliseconds when the packet actually arrives, I can tell you where the packet should go, right? So the orders can be done very, very fast. And just jump to the last one, is that we do hardware acceleration. So some components, again, in the 5G network, actually, there's very networking stuff, and they're not all done in software. So the question is that they're all just packet processing. Why don't you move them into the switch? The switch can do all this work, but not everything. 90% can be done in the switch, 10% has to be done back in the control plane. So you need a protocol to move things back and forth. Whatever I can do in the network, move them back to the control plane, and then back and forth, right? So the key thing is that I can do stateful migration on the switch, right? So when we did the evaluation, the key thing is it robust? So we have to run the real network, we have a 5G testbed running, and then we just basically constantly move the flow back and forth. Basically, there's no impact. If you do it well, you can have packet loss, you can out order, it will still maintain the same performance, and then you can benefit from the hardware acceleration, right? Okay, this is my last slide. Okay, just a quick shout out to all the people who really work with me on this topic. Many of them have graduated, a small number is still around, right? Okay, thank you. bit of time for questions, if there's any. So I guess we have some time for questions.
Yeah, very nice talk. So I think the config word is very nice. I read that paper. I just wonder, have you ever tried to test a config with package spring? How did that work?
Test config
With package spring, how does it perform? with package
actually, one of the
spring?
things that we are looking at, so the package spring, I think that the detail comes, right? The traffic load will determine how much packet reordering, and some papers assume that packet reordering can somehow be handled. Like you can, once you can hide all the out of order arrival, packet spring is great. But in practice, if you cannot handle some of them, then the performance drops. So it depends a lot on the way your traffic load works. So one thing we're actually thinking is that we combine Conwave and package spring. Think of Conwave as one example of a package spring, and then see whether they can combine it in some way. That's what we're kind of thinking. Yeah. So okay, yes, compare, but we found that the behavior is very sensitive to your traffic load. Yeah. So it's very hard to compare in some sense. Right.
Hi, thank you for your great talk. So I'm wondering, because you have touched on a lot of different areas, and I know that they all use like programmable network, programmable switches. How did you actually get into like those various different areas? Like how did you find those problems to solve, but all using like the same technique, same technology?
You mean how do I get into using P4, or how do I use it to
No,
solve?
I mean like, so you get like the P4 skills, but like how do you find problems that
Oh.
can actually be solved by P4, and they're like so wide areas of problems?
I guess it's always this is the research problem itself. How to find a good problem, right? So at the high level, I ask myself two questions. One is sometimes I feel like people use the P4 because they have a switch, and I think they probably just try to squeeze their problem into the switch. I think you want to find a more natural problem. What is the switch really good for? Certain things are not very good for. Even though I love the switch, but not all problems can be done by the switch. So you ask yourself, is this the right solution? Is it a natural solution, right? So I want it to be natural. Second, you want a problem that basically solves something important. So ask yourself, is this a problem that is worth solving, right? But sometimes people do agree, I think it's important, I think it's not, but I have to convince myself that the problem is interesting, important, and P4 is the natural solution, right? So I guess be more open-minded. Switch is always, I like it, but there are always other ways to solve the problem. So the other way is the natural one, you should pick the natural one. My tendency is I have a hammer, everything is the same, right? But you have to be honest with yourself. This is not the right solution. Try something else.
Thank you very much.
Hi, thanks, Major. Thanks for the very exciting talk. But my question will be a little bit high level. But given that Tofino has been discontinued support, what do you see on the future of programmable hardware? Because if there's no vendors making these devices, how can we basically keep innovating? How we rethink about the switch or the in-network application, especially?
Yeah, I guess it's a hard problem. Let me give you again two sides of it, right? One is let's give you the positive one first. I mean, I have been looking at similar problems since the 90s. So of course we go ups and downs. But I think the problem is that you want it to be programmable, right? I think the problem doesn't go away because you have no platform, right? We really want it, and it's very interesting, but a lot of problems to solve. So that part I think is fixed. All we need is a platform, right? So platform P4 is really interesting, useful, and we all love it, but unfortunately, the industry is what it is. So in the meantime, we still can use it because it's still available, and we still use it in the lab to solve problems. Look at other platforms. They have other strengths and other weaknesses. So again, we just have to live with the environment we have, right? So be flexible. And at the end, software is fine. You can always use software to solve the problem. All one is programmable. Like, don't get too stuck with the platform. Right? Choose the best one. That's what the most suitable. And you always think positive. Maybe further down the road, some startup hardware vendor will come out with the next great things. We all hope so.
Thanks.
So I wanted to follow up on what Chow just said, and we were talking about this earlier, that this is a really important area, but of course it needs to be validated with real switch platforms and so on. But we have other programmable components in the network, like smart NICs and DPUs.
Exactly, yeah.
So do you have any comments on what we have learned from the past on looking at programmable switch platforms like Tofino and P4 language? How are you seeing this being applied to these other...
Recording in progress.
Okay. I think two parts. One is, I guess, the technology. Of course, you want a technology that is good, as powerful. Because there's actually another hardware platform that is so-called run to completion. Very fast. Some of you know about it, right? But there's no open source. That's actually, think of it, the Tofino is pipeline based. Every log step, something happen. Another one is that you actually have many mini processes on the switch. You can write normal program, but it's extremely hard to have the timing correct because you cannot pick it out of the way. So that one is around. I think many companies actually use it internally. We just don't get a hands on it because, if you work with Huawei, maybe they have, or even Cisco or Broadcom, they have, but for academia, a lot of us don't have access. So I think, how to put it, technology is part of it, but I think one of the success of P4 is that they build a community. So I think if you have a sufficiently big community, that helps a lot because people, why the open source is successful, because people can share their ideas and share the code. So I think the next platform that comes out that can build a reasonable sized community, that will help a lot. The DPUs, a lot of them, I think we don't go around, we don't work together on some common. Ideally, there should be another P4 type that covers many of the DPUs. They don't help a lot too, but they're kind of fragmented. You use one, you'll start with the one with the specific thing. So that makes it very hard. Maybe you want like a pizza or the equivalent of all the DPU. That will help a lot as well. So let's hope someone does it.
Thank you so much, Professor Chan. Please join me in thanking Professor Chan for his excellent keynote.